Sushruta and Charak. So let me begin. This is Sushruta Samhita was written some 600 BCE. Now, as I said, take Om. What is BCE? So far we were listening to hearing the word BC, before Christ, then AD, Anno Domini. But then I came away, they said, no, we'll replace it with some other word which appears more secular. So if you go through the internet, you will find another word, BCE, before current common era. So now this term is changed by some people. Now we can call it before common era. Okay. So it is 600 before common era when this father of surgery, Sushrut, he wrote Sushrut Samhita. And these are some of the text which was written. Now, this was not written 600 BCE. It was written much later to it, but it was stored, saved, preserved. It was on palm leaf. Now, these are some of the pictures which you find whenever you refer to Sushruta Samhita. These things are preserved at Los Angeles County Museum of Art. Okay. And so this is about Sushruta Samhita. Similarly, Charak Samhita, this is about the Ayurvedic medicine. Uh, this was written some 200 BCE, but the need of medicine through our older scripts, this was in Arthaveda. From there it started and it was somehow brought to prominence by Maharshi Charak. Then, now, these are the fields which is related to medical science, which is very much needed. But mathematics, which was not much needed at that time because our need was food, clothing, and shelter. Here comes, say, Madhav series. Now, all of you must have studied sine, cosine, and tangent series. But you can find the infinite series expansion of all these trigonometric terms. In my school days, I never heard the word Madhava, but it was all sine, cosine, and tangent. When I started reading more on this, I realized that first, or rather, the historians, scientific historians, realized that it was first created by Madhava. Now you can read here an Indian mathematician and astronomer, Madhava of Sangamagrama, 1350 to 1425, the founder of Kerala School of Astronomy and Mathematics. Now, this was in India so long ago, and today, if we ask school children, do they know? They are not even interested in trigonometric series because it is mathematics and appears to be complicated. But long, long ago, our ancestors did this work. Now, this was picked up by the other prominent scientists of the European countries. One was Gottfried Wilhelm Leibniz from Germany. You can see here. This gentleman, 1646, a great scientist to 1716. His contemporary was Sir Isaac Newton. Now, both worked on infinite series, and but the mention of Madhava series was I have not seen anywhere, but it is there in the even the European libraries, and we too have it. But our students need to know this. Now, these two great people, scientists, discovered calculus at the same time. Now, some facts about their at that time what happened. Calculus independently. Both had different notations. And when they wrote, finally what happened? Sir Isaac Newton first published his Principia Mathematica and then the calculus theories. Leibniz objected, saying that I was the first who did it and wrote to Sir Isaac Newton. Both had bitter fights. Subsequently, Sir Isaac Newton became the chair professor, and then he ensured that his work remains at the prominent level. Now, we need to know the There's nothing wrong. You need to know the psychology or the behavior of these great people, not merely the outcome of their work. So I read both them in quite some time and to quite depth to understand how they spent their later part of their life fighting on the claim of calculus. So let's upon some European scientists how they are related to Indian work. Now you have seen Madhava's infinite series is related to Leibniz work. Then, if you study at later stage, 1870s, Leonhard Euler, then you will realize he is one of the biggest mathematician who invented complex number series. Then Gauss, he developed series, but initial of all those was Madhava of India. Now, I have a question for you, which we will answer gradually. This is what is your take home. Whether dry air or wet air is heavy, which one is heavy? Now, I request the organizers to give a chance to any one student to respond to this question. May I request so? Please let any student reply whether dry air or wet air is heavy and why.
Yes, somebody please give the answer. Sir has asked a question.
Sir, wait air. Sorry.
Okay, your good name, please.
Sir, myself Hemant Gabne.
Okay, okay. Now, please put off the mic. Now, let me answer. Okay. Now, this is a very general perception that wet air is heavy because we try to simulate using, if we take a handkerchief, weigh it dry, we'll find some grams. And if we put it in a bucket of water and then take it out, squeeze it, and then try to measure its weight, it will obviously come more than its dry weight. So we say wet handkerchief is heavy. That simulation we extend to air also and say that wet air is heavier than dry air. Now let us see further how it can calculate it or not. Now here see composition of dry air near sea level. Why sea level? Because there the maximum pressure is exerted by the column of atmosphere. So let's see the maximum component is of nitrogen 78%, oxygen 20.947%, argon 0.934%. Then carbon dioxide, you can see the value is coming down, and if you see the entire list, the contribution of all other elements are very, very, very small. So if we want to have simpler calculation, what we can do is, let's have nitrogen 78%, oxygen 21%, and then close. Rest we'll leave everything so that we can do simple calculations. Now, molecular weight of nitrogen is 28, oxygen 32. Let us do the fractional weight. So if we take one unit of air, what will be the weight contributed by nitrogen in 1 unit of dry air? This will be multiplication of these two numbers, that is percentage volume and molecular weight. So multiply these two, divide by 100. This comes out to be 21.9. Similarly for oxygen 6.7, argon 0.4. And this will give us the approximate molecular weight of dry air. So all students, please remember the approximate dry air's molecular weight is 28.9. Now let's go a little ahead. Let's compare. What we are trying to answer is, what if the air is wet? Wet means we are feeding moisture in it. So here, let's see the same for moisture. Hydrogen, 1 molecular weight. H2, 2 molecules, 2 atoms, so it is 2. Oxygen, 16 into 2. You can see its molecular weight. Let's add all together. H2O. Its molecular weight is 18. Any doubt? I believe there should not be any doubt. Now let's compare. Dry air is having a molecular weight of 28.9 and and H2O, moisture, is having a molecular weight of 18. Now my question, let's go back to our question. The question is, what is the comparative weight of wet and dry air? So in a dry air parcel, imagine an air parcel of the shape of a balloon. So in the atmosphere, take a balloon, fill it with dry air. So that is a air parcel, and then remove the outer membrane. Imagine that dry air. Inside the dry air parcel, we are feeding moisture. So when we feed moisture, equal